Good morning, good afternoon, everybody. So today we're going to have a webinar on HDF5 and more specifically on using PyTables Python library for working with HDF5 files. So HDF5 itself is, well, it's the fifth version of the hierarchical data format library, and it's been around for quite a while. So the development started in 1987. And now we are on version 5, which has been around for about close to 25 years now, I think. So what HDF is, again, stands for hierarchical data format. And it's a specification and a library for working with very large data sets. And as the name suggests, you can have hierarchical data organization inside the data set. So you can have essentially subdirectories and folders and folders inside folders, and then multiple data set arrays, for example, inside a single file. So I've been using myself HDF5 for quite a while, so since probably the late 1990s and especially in the early 2000s, primarily from Fortran. So initially HDF was written for Fortran and C, and now there are APIs for pretty much any programming language. So today we're going to be focusing on the Python interface, and more specifically, we're not going to talk about the official HDF5 library for Python, which is out there. We're going to talk about a different implementation which focuses on speed and has some other nice features called PyTables. They're actually, so I have a link, so the notes that I pasted into the chat, and Marie, I see, keeps posting them into the chat for newly joined attendees. So if you go to the notes, and here's, by the way, the URL for the notes that I can display on my screen. So if you go to the notes, there are lots of links there. And then one of the links, so let me just paste it just in case into the chat. One of the links shows a comparison of PyTables versus HDF5. So there are two sources. One is the official HDF5 Py webpage, and the other one is the PyTables webpage. But basically, they tell you about some differences between these two projects. But today, we're not going to talk about H5Py official HDF5 library at all. We're going to focus specifically on the PyTables library. So a couple of words on installation, how to install PyTables. It's actually fairly easy, but it depends on your operating system, on your process architecture, and mostly on the way you like to install Python packages. So if you install Python via, if you install Python in such a way that you have pip available to you, and then you install Python packages via a pip Python installer, then you can use it to install PyTables. The only thing is that you need a couple of dependencies. You need to install first the HDF5 library, so the C flavor of the HDF5 library, and it's available, as an open source download or as a binary, precompiled binary for many different platforms. And you also need the NumPy package, because today we're working a lot with large arrays, and essentially all large data structures, large arrays inside PyTables are stored with NumPy library. And so once you have those two dependencies installed, you can simply go and install the PyTables library. So if you use pip, for example, then it's actually called tables, not PyTables. If you use conda, in conda, it's called PyTables. In conda, you will use something like conda install PyTables, and then in pip, it's pip install tables right here. Where is it? Pip install tables right here, install tables. And also, so before I say pip install tables, I also provide the link to my HDF5 installation directory. Anyway, so depending on your platform, your operating system, your process architecture, and on the way you like to install Python and its packages, there will be a number of different ways you install it. So here's, for example, the complete pipeline, how I install it on my MacBook. So on my MacBook, I like using the Homebrew package manager, and I simply use Homebrew to install Python. Then I modify my path to point to that version of Python. Then I install the HDF5 library, just a single line. In my case, very, very easy, just use the package manager. Then I create a virtual environment into which I install the tables library. And then I install tables, as well as some other things that are nice to have, but they're not necessary for working with the PyTables library. All right, so today I'm going to show you all demos on my computer. So to activate demos, I actually have to start the virtual environment. But then on your own end, you can install PyTables fairly easily, using either pip or conda or something else. So on the Alliance classes, we have PyTables actually installed, so you don't have to install anything. And the way you load PyTables is you have to load the HDF5 module, the Python module, and the SciPy stack library. So SciPy stack includes things like NumPy and PyTables library inside, right? And then you can just start using. So no need to install anything on clusters. Just load the necessary modules. All right, so today I'm going to give you, so today's webinar is going to consist of 3 parts. I'm going to give you first the classical introduction to PyTables. I'll actually go follow closely the official tutorial, even though I don't like the example. I'll have my own example. And then in part 2, we'll talk about working with multidimensional arrays. I'm going to show you some examples of very large arrays, how we can easily save them into an HDF5 file and then enable compression and visualize these files. And then if we have time, at the end, I'm going to talk about simulating a file system inside an HDF5 file with the PyTables layer. All right, so let's go to the demo. So the way HDF5 organizes data is, as I mentioned, is hierarchical. And everything you write into an HDF5 file is stored under root. So it's actually very similar to the Unix file system. So everything you put inside is stored under root, so / or root. And then what kind of things you put in there are essentially 2 things. So groups, and they are very, very similar to Unix directories. So think of a group as essentially as a directory under which you organize your data, your data set, your arrays, etc. And then you have nodes, which are very similar to files. So a node could be a table, could be a text file, could be an image file, could be a large array, etc., etc. And so a single HDF5 contains all these objects, but everything, so all groups and all nodes, as you will see in many examples today, are stored under /. So let me actually drag these out of the way so I can actually see my notes at the same time while I type commands. So it's all going to be live demos. So I'm going to activate my PyTables environment, and then I'm going to start my Python. And then I'm going to import tables as TT. So TT is the alias. And similarly, I'm going to import NumPy because you need to NumPy to actually work with arrays inside these HDF5 files. And then, so now we are actually going to jump straight to a class which lets us describe a table and store this table inside an HDF5 file. So I realize this is quite a steep learning curve, but I don't think there's any way around it. So essentially what we're going to do is one of the things that the PyTables library provides is a class called isDescription. And essentially it's a way to describe data, to write this data into a table. So what it lets you do, this class lets you create columns and describe data in these columns, and then these columns will be written, as a bunch of rows into a table inside an HDF5 file. And the reason I'm using this is because I'm going to initialize my own class. So I'm actually copying and pasting the commands from the nodes. And so this is probably the most complex command you will see today. But essentially, what I'm using the isDescription class as is a parent class to initialize my own class star. And what I'm doing here is, so in this example, I imagine that you are observing the sky and you want to create a catalog of stars, and basically you have several observable properties of each star. So you have perhaps you give a name to each star, and you have right ascension and declination. So these are the 2 angles specifying the position of the star on the sky. And then perhaps you have 3 colors, so white, red, and blue. Perhaps you have parallax, which is the inverse measure of the distance to the star, and then have proper motion, which is the projected onto the sky inherent motion of a star as it flies in space with some 3-dimensional velocity. So the projection of that 3D velocity onto the sky as it moves during 1 year across the sky. And so usually parallax is measured in fractions of an arc second, and proper motion is measured in, well, maximum it's a few arc seconds, but usually it's a fraction of an arc second, so very small numbers. Anyway, so what we're going to do is we're going to create a table, and then each row in the table will represent a star, and these are going to be the columns, right? And then I created a class called star, which is the child class of this isDescription class provided by the PyTables library. So you don't need to understand the details. Basically, this is just a way of quickly organizing a table inside the HDF5 file. And then next, what I'm going to do is I'm going to create a file. So I'm going to call this file catalog.h5. So h5 is the standard extension for HDF5 files, catalog.h5. I'm going to open it in write mode. So HDF5 files, as you will see, you can read them. You can open them in write mode, in read mode, as well as in append mode, where you can both read and write data. All right, and then we'll also provide an optional description, just call it stellar catalog. Okay, so here we open the file, and then inside the file, we're going to create a group. So a group, think of a group as a subdirectory, essentially, right? So under root, so whenever you create, a node or a group inside an HDF5 file, the first argument usually will specify where you create that object, and we are creating it under /, right? So under root, so it's going to be, in the top level directory inside the HDF5 file. So we're going to create a group that is called data. And the observational data, again, it's an optional description. So the group name has a handle, so it's passed, the output of this command, create group, is passed to a handle that we're going to be using in the next few commands. I'll just call it G1, right? So it's just a variable name. And if I look, so if I go into the same directory, actually, let me make it slightly bigger. So if I go into the same directory, you will see that now there will be a new file called catalog.h5. So I go here and do ls-t. Now you see that there is this new file, catalog.h5, and this file is currently empty because we just opened it for writing. We added a group, but we have not written anything to this file yet. And now inside this group G1, we're going to create a table. So I'm going to say create a table. The first argument usually tells you, once again, where you're creating this object. So inside the group G1, inside the subdirectory G1, we're creating a table called stars. And then to fill in the rows and the columns of this table, we're going to be using the class star that we defined earlier, right? So this class star will give us access to 8 columns. And then optionally, you can provide a description that I call all stars, right? But inside the HDF5 file, inside the G1, inside the G1 group, so it's actually inside the G1, inside the HDF5 file is going to be called data. So inside /data / you will have an object called stars that will contain our table with all the stellar properties. Okay, so here we created the table, and then now we can actually print some information about the H5 file. So you can say, for example, print on the handle that we use to when we open the HDF5 file, so H5 file, and that will give us some information about the internal data organization inside this file. So you see that there is the forward slash to the root directory, right? So everything is sitting under / like in Unix file system. And then we have a group, so a subdirectory called data. And then inside the subdirectory called data, we have a table called stars. Right, so you can see that this table currently it's empty. There are no rows. We haven't added any data. And if you call H5 file handle without print statement in Python, I'll actually give you a little bit more information. It will also give you the description of all the fields of all the columns inside our data table stars. All right. So let's actually start filling in this table. So I'm going to use a couple of libraries. First of all, I'm going to use a random library from Python because I'm going to be filling, the numerical values in the table. I'm going to be assigning randomly using some, random numbers from uniform distribution. And then I'm also going to use this library called random word. And this library is really interesting because it lets you pick up random words from the English language dictionary and put some constraints on this word. So for example, we could do things like this command lets us pick only nouns, and the length of this nouns is going to be between 4 and 8 characters. And I'm going to be using these, so you see that every time I run it, it gives me a noun with 4 to 8 characters, and every time is just a randomly picked noun. So I'm going to use these nouns to fill in the names of the stars. And but before I do this, I actually need to call table row and assign it to a star. So this is essentially going to be a pointer to the tables row instance, right? So having access to lowercase star, using lowercase star will actually give us access to the instance of this table, so we can actually use it to fill in the rows in the table. All right, and then I simply have this loop where I goes from 1 to 100, right? And here we're simply going through 100 rows, so 100 stars. And then for each star, I'm randomly filling its name, its right ascension, declination, white, red, blue colors, its parallax and proper motion. And then once I have the values for these 8 columns, I simply add them. I say star append, so star is a row, right? And then I add 1 row at a time. So let me paste that. And once I do this, now you can actually see it takes a couple of seconds. It just generates all these numbers randomly. And now if I do table shape, you will see that it still reports that my table is empty. And the reason for this is because I need to write the table to the file, right? So table essentially, think of it as a pointer to the data stored inside your file. Currently, we haven't stored any data yet. So basically, you need to take all these information memory that we just created and flash it to the file. So now the table has 100 rows. And in fact, I can do something like this. Well, yeah, table shape will tell you that I have 100 rows. So now let me close Python, and I can simply exit Python now. So it's fairly safe to do this. Actually, I have not seen any problems with closing Python at this point. So the data is already written to file. But if you want, added security, if you want to make sure 100% that everything was written safely, you can simply pass the close function to this on this HDF5 file, right? So let me exit Python, and now if I do ls-l on the catalog.h5, you see that now it's 70 kilobytes. So it has all this data that we wrote about 100 stars, as well as some metadata, so some data description and some internal hierarchical data organization that you will see in every HDF5 file. So are there any questions at this point? So what we're going to do next, if there are no questions, we're going to reopen this file. So again, I'm going to go into Python. I'm going to import tables, PyTables library and NumPy library. And then I'm going to open this file, but this time I'm going to open it in append mode, right? And then now I actually have access to all data inside the file. So I can say h5 file, root, and then now you see there is data. So data folder under root, and then under that I have the stars object, right? So you can actually navigate, your data structure using this dot notation in Python, which is really, really handy. And then if I run this stars table, this object, if I print it, it just shows me, the basic information about, the columns and rows. So there are 100 rows, and these are the columns that I have inside this file, right? So there are many ways you can dissect this information. So you can, for example, say table columns, and that table actually haven't assigned the pointer to the table. So here's the pointer to the table, and now I can say table columns will give you some information about the columns. If I say table shape, it will simply tell me that there are 100 rows, right? Then you can access data in individual rows and columns. For example, for column, you can use it. You can access data providing the column name inside this function call like this, right? And notice that the name is actually, so when you inquire about the type, it actually gives me not string, but something different. So these are the values, right? So tabletop, novel, turtle, and etc. So those are random nouns. And notice that have these prefixes b. So I assume that most of you are not familiar with this notation. So what it means is it's actually not a string. It's not stored as a string inside Python, inside NumPy, but it is a byte class array. So each element in this array has length of, well, actually the length is whatever we initialized earlier, so some number of characters, but each character is stored as a 10-bit number. And the reason for this is because 10 bits gives us 256 numbers, and it's very easy to use this to encode all ASCII characters, right? So all ASCII characters I fill very easily into 10 bits. And the reason NumPy uses these byte storage but not strings is simply because NumPy tries to be as uniform as possible, and this is just a very efficient way of storing ASCII characters, right? All right. So let's take a look at the parallax column. So parallax column is a numerical column, and it has 100 parallaxes for 100 different stars. You can also access this information in a different dot notation. So instead of seeing table columns and then in the function call pass the name of the column of the variable, you can say table.columns.parallax, and then access it as if it was a NumPy function. And actually, in fact, underneath this is a NumPy array, right? So you see that all data internally inside this table is stored as a NumPy array. So very, very efficient way of storing data. All right, you can iterate through rows. For example, you can use this notation, right? So here's a table.iterate through rows function, and simply organize it as a Python loop. And here it just goes through all rows, and for each row, for each star, it prints all id variables. So really, really easy. You can also apply, functions like aggregate functions like min and max, for example, and a few others, right? So these are very useful. For example, if I look at the parallax column, you see that this is the smallest value of parallax. This is the highest value of parallax in my data set, right? So that means that I can actually issue a conditional statement. So here I have a list comprehension in Python, right? So organizing a new list that I call names, and this list only contains names of stars, the parallax of which falls into this interval, right? So between 3 times 10 to the minus 5 and 5 times 10 to the minus 5. So that lets me easily, subtract, extract only only those stars that have a certain range of parallaxes. And there are, about 10 or 12 stars that fit this criterion. So you can also have a condition specified as a string variable. So you can do something like this. Let's say we're only interested in stars that have their declination, so distance from this celestial equator greater than 45 degrees, right? So here we form the condition, which is a string variable, right? So this is a condition is a string variable, and then you can simply use it as an argument to a where function, right? So we say table where the condition holds true, simply print those rows, and actually print not the entire rows, but just the name and the declination. So when I do this, you'll see that all declinations are larger than 45 degrees, which makes sense. And of course, we're going to have more complex conditions. So for example, we can say declination is greater than 45 degrees, and the color of the blue color of the star is greater than 0.5, right? So basically, we are looking at northern blue stars, right? So it's a more complex condition. And again, the condition is formed just as a string variable, as a string. And then we simply go through all stars that satisfy this condition. So table where condition, and then for each star, print the name, declination, and its blue color, right? So here we go. So here we have fewer stars. And actually, let's take those stars and store them inside the names. Well, store their names inside the names array, actual names list, right? So names is just a list of stars that satisfy this condition. And then let's actually write this array. So here I'm just showing you how we can take an array and add it to an existing file. So currently our HDF5 file contains only the table of 100 stars, but now we're also going to add an additional array to this table. So to do this, I'm going to create a new group. So you don't have to write it under a separate group. I can write it under the main group, but I just show that this is possible. So I'm going to create a new group called cell for selection. And inside the HDF5 file, you will see this group as selection, right? So it will be placed under the root of the file system inside the HDF5 file. And then here's an optional description, northern blue stars. And then inside this group, so inside selection, we're going to create an array that will simply contain, will be an NumPy array containing the names of the northern blue stars, right? And here we'll provide the optional description. So let's do this. We've done this, and let me now close my file. So I'm going to say H5 close and exit Python. So now if I do ls-l on the file, you see that the file is a little bit larger because now it has this additional data structure. So an additional group called cell, and inside the cell group, selection group, I have an additional array of stellar names that satisfy this condition. All right, great. So you can actually examine the HDF5 file from Unix without, you don't have to go into Python. So when you install PyTables library, it provides you a very nice, actually, I think this is from the HDF5 itself. So if I say which HDF5, yeah, I'm pretty much sure that, yeah, it's just the HDF5 itself. So there's a nice utility called h5dump, which will simply tell you everything inside, stored inside the HDF5 file, right? So I'm just saying h5dump, passing the name of the file, And here we go. So here's the all information that was converted into ASCII and dumped into the terminal. So there's quite a lot of stuff there, right? So I can scroll up, but I can display this information actually in a little bit more concise format by using a different utility, h5ls minus rd, and then the name of the file. And so here's my data in a little bit more compact format, right? So it appears more like a table, right? But very easy to examine the content of an HDF5 file from inside, from command line. And notice, by the way, that even though I'm looking at all this data as text, inside the HDF5 file, all data is stored as binary, right? So HDF5 file is very, very efficient when it comes to data storage. So not only it stores data as binary, but it's also capable of compression. You'll see an example of compression very soon, as well as parallel file IO, et cetera, et cetera. All right. So let me go into Python, again, into Python. And then let's try to play with the data a little bit. So I'm going to import tables in NumPy, and then we'll reopen the same catalog.h5 file in append mode. And then I'm just going to show you how you can cycle through all nodes. So a node, so here I'm simply saying for node in H5 file, print the node. And nodes in HDF5 file are basically any objects you put inside the file. So there could be groups, and they could be arrays, tables, et cetera, right? So here we see we have the following objects. So we have the top level root directory. Under that, we have data group as well as selection group. So inside the data group, we have the stars array of 100 rows, well, table of 100 rows. And then we have also a HDF5 array with 4 elements, which contains the names of the northern blue stars. And also specify, you can walk through a file in many, many different ways. For example, you can only walk through groups, right? Instead of saying, for node in a file, I call the walk groups function. So this will print only the groups. So there is root, there is data, and there is selection. I can specify nodes that are, let's say, inside the data group, right? So the notation for that will be list nodes, but then I specify that I'm only interested in nodes that are sitting inside the data group, so inside the data folder, right? And I'm only interested in tables. So let's check that. And there's a single table inside the /data group. Okay, so let me show you how you can. So here in my notes, I also show how you can write attributes to the file. So these attributes, for example, could be attributes of a table, right? So here are some examples. I'm not going to show them, in more details because we don't have a lot of time, but you can follow these examples later on. And also here are a few lines that show how you can add additional data to an existing table. So here I'm going to initialize the description of the table and all the libraries that I use to write into the table. And then I'm going to add 50 additional stars. So exactly using the same syntax as before, but in addition to the initial 100 stars, I'm adding 50 stars. And then now if I say table shape, it will tell me that I still have 100 stars. And the reason for this is because table points to the data on the disk. So I need to flush this data from memory to disk. Now, when I do table shape, it shows that I have 150 stars. All right. And of course, you can modify this data as well. So for example, if I want to override some data, change some data on the table, I can do this fairly easily. So here's, for example, a pointer bodies to the names of the stars inside the table. So if I print bodies, well, actually, I need to print it as a NumPy array. So here are the 150 names, and then I can easily modify them. For example, I can do something like this, right? And then now I have the new names 1 and 2 inside the table. So here I have 1 and 2. And of course, everything is super, super easy. So to actually write this data, I need to flash it back to the table. And then I can either type, F5 close or just exit. And usually, in my experience, it closes fairly safely. But if you, want double security, make sure that you run the close function. All right. So this is the end of part 1. And now we're going to jump into more interesting territory. We'll actually start working with multidimensional arrays. And the way I decided to do this in this webinar is instead of initializing randomly generated arrays from scratch, I'll actually read some data from another file format, from a netcdf file, which is a competitor to HDF5 format. So I'm going to read the data from the netcdf file, and then I'm going to write this data into an uncompressed HDF5 file. It's going to be large because it will not use any compression. Then I'm going to show you how to enable compression so the file becomes much smaller in size. I'm going to append a second array, read this file back in Python, remove the second array, so show you that you can actually remove arrays, in variables and tables, etc., from an HDF5 file. Then I'm going to create a soft link that is very similar to a soft Linux link, but this time it's going to be inside an HDF5 file. And then I'm going to create an XMF descriptor for the array, and we'll actually visualize this array inside ParaView. So the data set itself, if you want to play with it on your own, here's the data. So it's in the notes, but to download the data, you will run a command similar to this one. So here I'm downloading the data, and from this data set, I actually need just a single file called mandibulb 300.nc. So I'm going to say yes to override. So basically what it does, it gives me a 1 megabyte file. And this is an etcd file that I'm going to be reading into Python, and then I'm going to store this file as a HDF5 file. Let's initialize Python and then initialize the tables in NumPy libraries. And then I'll need to, in order to read my netcdf file, I actually need to import the netcdf library as in C. And so the file I'm going to be reading is sitting inside the data directory, so the mandibulb 300.nc file. And why it's called mandibulb? Because it's a three-dimensional mandibulb fractal, so you will see it in a few minutes, visualized in ParaView. But first, I'm going to read it in netcdf. So the file is sitting inside this variable, which is actually essentially a NumPy array, right? It's a 300 by 300 by 300 array that stores my variable. It's of type integer 64. Well, actually, sorry, the coordinates of type integer 64, but the variable itself is actually of type integer 32, right? So integer 32, single precision integer, and it's a 300 cube array. And then in order to print this array, I can do it in many different ways. One of them is to do something like this, right? So actually not this. Let me see how I can print this array. So ds, actually ds is data set itself. So here's the shape of the array. And if I print the array, I can do something like this. Right, something like this will give me access to the entire array, or I can specify explicitly that it has 3 dimensions, right? But basically here I'm just, subsetting the entire array out of the array. So it'll just print back the entire array. Of course, it will truncate it because the array is very large, right? But the point here is that you can actually use this notation, let's say, to print, only 3 by 3 by 3 corner of this array, and you can do this very, very easily. All right, so let's actually write this array into this NumPy array into an HDF5 file. So I'm going to call the file uncompressed.h5 because first I'm not going to enable compression, and you will see the result is the file is going to be very large, right? So here I'm creating a new file, opening a new file in write mode, and then inside this file I'm going to create a group. I'm just going to call it G1. So under / inside the file in G1 group, I'm going to create a new array called stability. So this variable will be called stability inside the HDF5 file, inside the G1 group, right? So I'm creating this group, and then I'm simply, so here, by the way, I already wrote the data to the file. So here I'm using ds numpy array, right, that I read in netcdf before, and I'm writing now into the HDF5 file, and then I close the file. I will exit Python. And now I do ls -l on the file size. And as you can see, the file is much, much bigger than the original netcdf file. So the original netcdf file was 1 megabyte. It was a highly compressed netcdf file. And then when I write it uncompressed into HDF5, it's 103 megabytes. So actually, if you do the numbers, so it's a 300 cube array, this many numbers, and each number is 4 bytes, right? So 108 108 million bytes, so 103 megabytes, right? And that's exactly, actually divided by this number to show megabytes. So it's exactly 103 megabytes, right? And this is exactly what we get for the uncompressed file size. So how do we enable compression? Very easy. But let me, to do this, I will need the original array. So let me quickly paste the lines to read the original NumPy array. Right, but this time I'm gonna, before I write it to a file, I'm gonna create the compression filter. So I'm enabling compression, the zlib z library compression, and I'm going to be using a modest level of compression. So this number can go from 0 to 9. So 0, no compression, 9 is the highest level of compression. So I'm going to use some reasonable number in between. So I created the compression filter, and then I open a new file in write mode, and this time I call it compress.h5. And this time I'm passing a filter, a compression filter that I just created in the previous line, right? So I do this. Inside this file, I create the G1 group, and into this G1 group, I write my DS data array, right? And I call this variable stability. And then I simply close the file. So now when I exit Python and I look at the size of the files, now my compressed file is actually much, much closer to the size of the netcdf file, right? So it's 1.4 megabytes. And remember that the netcdf file actually was 1 megabyte, and that was only simply because I enabled very, very high compression in netcdf. So if I enable a high compression that, then compression level 5, then it will give me a slightly smaller file size than 1.4 megabytes. All right. So let's actually add a second array to the same group. So I'm going to enable load the libraries, go back into Python, load the libraries. I'm going to read the file in append mode, right? So here I'm reading the same compressed HDF5 file in append mode, and then I'm also enabling the compression filter. And now I'm creating a random array. Why not? So now it's a random 100 by 100 array drawn from a Gaussian distribution, right? So here's my array A. And then I simply write this array into an existing G1 group, and then I close the file. Oops. Let's see. Oh, okay. And I close the file. So now the file, if I look at the size of the compressed.h5 file, now it's slightly larger. Previously, it was 1.4 megabytes. Now it's 1.5 megabytes, and that is simply because it contains the second array. So let's read this file. Step back into Python. And now I can read this file. So I'm going to open this file in read mode. So opening this file compressed.h5 in read mode. And now I'm cycling through all nodes in it and just printing some information about each node. So you see that now under / we have the G1 group, and under G1 group we have the 300 cube array, as well as a 100 squared random array that we added later on. So you already saw some ways to dissect data using the dot notation. It's really, really very handy. So I can do things like F1 root, and under that I have G1 group, and under that I have two arrays, stability and A. Let's say I want to look at the stability array. Well, here's my array. It's actually very large, right? Because it's a 300 by 300 by 300 array, but I can certainly dissect a point of it. For example, I can print just one of the corners of this array, and you see that all numbers are 2 by 2, 2, 2, 2. But of course, not all numbers are 2. So if you can apply the max function, and it will show you high values of this array, right? Which is actually, cannot do it like this. Maybe I can do it like this. Yeah. No. Well, I have to look up my notation. I just don't remember how I used max before. But anyway, you can run the max function on this array. I just don't remember the syntax. It's in the early example that I showed you. So anyway, and you can extract a lot of information about this arrays. For example, the title of this array, right? So it has no title. We didn't provide any description. Then dtype, so type of variables. So each number in this three-dimensional array is integer 32, so single precision integer. And you can even do things, how much memory does this array take when you actually load it uncompressed into memory. And here's, the familiar number, so 103 megabytes or 108 million bytes. All right, let me close Python and let me open Python and then reopen this array in, this file in append mode, so I can actually modify things. I'm opening this array, this file with two arrays in append mode. And then I'm going to show you how you can remove an array. It's super, super easy. You see, just call the array dot remove function. And now if I do F1 dot root, let's see if it'll show me just a single array. Yeah, it just shows me a single array, right? So if I try to expand it, it doesn't show A anymore. It just shows stability. So here the point is that now we actually have just a single array. So I have that function h5ls on compressed file, and it should tell me, actually it shows a lot of stuff, but it should tell me that now inside G1 I have just a single variable stability because we just erased the two-dimensional array in Python a minute ago. All right. So finally, let me visualize this this file. So what we're going to do is we're going to visualize the file compressed.h5, which contains our highly compressed 300 by 300 by 300 array. And unfortunately, you cannot. So my favorite visualization tool is PyView. And unfortunately, you cannot load HDF5 file directly into PyView. And the reason for this is because HDF5 files store arrays, whereas PyView, what it wants an array on top of some discretization, right? So essentially, I mean, I guess you could code PyView in such a way that if it sees that it reads just a single array, then it simply puts the array on a Cartesian mesh. But PyView doesn't do it for whatever reason. So PyView actually needs to have an underlying mesh. And the way to do this with HDF5 files is actually to provide a second metadata file in a special XDMF format. So what I'm going to do is I'm going to create a new file called compress.xmf. So .xmf extension stands for XDMF file format. You can Google XDMF format, XDMF for HDF5, and you can read more information about this. So using XDMF as a file descriptor for HDF5 files. But basically, I'm going to create this file, and I'm going to paste the following into this file, and then I'm going to open this file inside. So I'm opening it inside Emacs, right? And into Emacs, I'm just pasting the lines from my nodes, right? And what these lines do, they simply tell me that I'm using the data from, for the array, I'm using the stability array from compress.h5 file, and inside the file is sitting inside the G1 group, and then it's going to be placed on a uniform Cartesian mesh. There's going to be, these are dimensions, and these are the spacings between adjacent planes in X, Y, Z. So basically that means that it's going to be, when I visualize it, it's going to be a cube, not a rectangle, elongated in some dimension, but it's going to be a cube, same size in all three dimensions, right? So anyway, so here's my file that I just created. The file I'm going to load into PyView is compressed XMF. So this contains the description, right? So how I place my array onto the Cartesian mesh, and the Cartesian mesh, the data for the Cartesian mesh is actually stored inside this compressed.h5 file. So let me open this guy inside PyView. So I'm going to navigate to the to my temporary folder. So it's in Home, TMP, PyTables, and it's compressed.xmf file. So I'm reading it as XDMF file, and here's my data. So not terribly exciting because we need to actually, let's look at the outer surface and color it by our stability variable. So again, not terribly exciting. Let's bring up a contour, draw a contour for this value somewhere in the middle of the stability variable. And here we go. So now you actually see a three-dimensional fractal, right? So this is a three-dimensional fractal, which you can light in some dramatic ways. For example, you can put the light, move the light to the bottom. So you actually see very nice shadows. Very nice shadows. Let me just do this. If I just put the light at the bottom, you see very nice dramatic shadows. But basically, this is the fractal that we read as a three-dimensional array from an etcdf file, and then we stored it inside a compressed.h5 HDF5 file. All right. So are there any questions so far before we go to the very last section? I see. Oh, sorry. There is something in the chat. Thanks, Alex. That was very useful for me. Okay. Yeah, you have to leave. All right. So are there any questions? Before we jump to the last section, we will talk about simulating a file system inside an HDF5 file. All right, if there are no questions, let's go to the last section. So nice addition to PyTables library, it allows you to use HDF5 files as containers for data in essentially any format that can be written and read from inside Python. So here I'm going to show you an example with image files, but of course, this doesn't apply only to image files. This can apply to many different file types. They can read and write from inside Python. So what I'm going to do is, in this example, I'm going to start with the following file, tascany.avi IVIF. So IVIF, this is a new, newish, highly compressed bitmap format for, well, bitmap is actually lossy compression, sorry. Similar to JPEG format for images, But this format is basically very, very efficient. And here I have some, a Tuscany landscape photograph stored inside this file. So here's what it looks like. Oops. Here it is. And what I'm going to do now is I'm going to use image magic and some bash scripting to randomly crop 20 windows. Each window is going to be of size 300 by 300 out of this image. And then I'm going to write those images inside, I'm going to store them inside an HDF5 file. All right. So before I do this, let me actually show you how you can store a simple text inside an HDF5 file. So for this, I'm going to go back into Python. And then I'm going to read my tables, PyTables library, as well as an additional module called file node that let me store data as any type of data as nodes inside HDF5 file. And then I'm going to open a new file for writing. This file I'm going to call storage.h5, so it's a new file. And then into this file, let me open a new node inside this file. So I'm going to say file node, new node. So inside F1, inside this HDF5 file, I'm going to create a new node with a name text file. And then this text file, I can actually inquire, ask PyTables library about the type of this node text file, right? So I'm going to say this node. So here I'm actually giving the absolute path, right? So very, very similar to Unix absolute paths. So this object inside my HDF5 file, please tell me its type, what it is. And it says it's file, right? So basically it means I can write, anything I can write into a file, I can write into this node. And first, let me start by writing simple text. So here I have some ASCII string, right, which I actually encode as Unicode, UTF-8. And then you also need to supply the line break because HDF5 can, the PyTables library doesn't provide anything of its own for a line break. So I actually need to encode the line break, to put the line break by hand, right? But anyway, so here I have an ASCII string that I convert to a Unicode string, and then I write it into this file just using, fnode write function. So I'm going to add a couple of more lines. The second line, I'm going to encode not as Unicode, but just a straight ASCII. And then the last one, I'm not even going to encode, right? So just added 3 lines. Then I'm going to call fnode seek0 to rewind back to the start of the file. And then I'm going to simply print all the lines inside the file just to show you that it's possible, right? So here are the 3 lines that I just wrote to the file. And then let me close the node. And then let me close the file. And then exit Python. So now I have a new file that is called storage.h5, right? Which 68 kilobytes. So notice that most of it is not these lines, right? These lines are just a few bytes, but most of it is actually metadata, organization of data that you will see in every HDF5 file. But beyond those 70 or so kilobytes, you have actual real data, which right now is just 3 lines of text. All right. So if I want to display this data, I can also, do things like ptdump, for example. So actual ptdump not shows the data itself; it just shows, the organization of data inside the HDF5 file. So previously I showed you h5dump command as well as h5ls command. So those come from the HDF5 library itself, whereas ptdump command comes from the PyTables library. So it's a Unix utility, Linux utility that's provided by the Python PyTables library, right? And it just tells me that I have, so inside this file, I have root, and under root, I have, a text file with, I don't know, 64 characters, I guess. So I'm not sure what the 64 refers. All right. So let me go back to Python. Let me add another line to this data. Let's see. I will open this file in append mode. And then I'm going to add some data to this file. And actually, to do this, the node itself will need to be open in E+ mode. So that means a read and append mode. And then I'm going to add a 4th line to this. So using the same syntax as before, fnode.write, I'm adding a 4th line. Then rewind to the beginning of the file of the node inside my HDF5 file, and then print all the lines. So now it's going to print all 4 lines. Well, great. Right? So I exited Python, and notice, by the way, because I didn't close the node and then didn't close the file, it gives me some warning. But in my case, it actually, I think it actually wrote the 4th line successfully. I strongly suspect so. So let me go back to my Tuscany dataset file. This file, so the Tuscany landscape, it actually has the width, the following width and the height, which I'm gonna store as bash variables, and then I'm gonna pass the following piece of code. So this is some bash scripting coupled with image magic for so I'm using the convert command from inside image magic to take out my Tuscany image file and then crop 20 randomly selected 300 by 300 windows, and then I'm going to use those as separate files. So basically, I just run this script, and what it does, it comes out those 20 images, and each image is called small and then to digits.png. If you want to see what they look like, we can just open one of them. So this is one of the images, right? I just randomly selected images, and then I'm gonna write these images into my storage.h5 HDF5 file. So to do this, I'm going to use the Python imaging library because I need it to actually read and write images from inside Python. So normally, if you deal with a standalone image, let's say image small00.png, so the way you read it from the Python imaging library PIL would be the following. So you're going to say import image module from the PIL library. Then you read that image from the file, and then you see image show, right? Oops, image show, and that will image show, and that simply displays that image in a window, right? But the way I'm going to write this inside HDF5 file is I'm going to go into Python, and then I'm going to create a new group called Tuscany inside the same storage.h5 file. And then I'm going to cycle through all 20 input files. And then I'm going to read each file. So here I'm cycling through all input files, right? So through all files small.png. And then I'm going to read each file. And then I'm going to create a special separate node for each file. So the node is going to be placed into the Tuscany group inside my HDF5 file. And then the only trick here is that I cannot use names like this, for example, small06.png, because the names of the nodes inside HDF5 cannot include special characters like dots, punctuation characters, and so on. So what I'm going to do is I'm simply going to remove .png, going to modify the name by replacing .png with nothing, right? So I'm going to simply call this small.06 and so on. I'm going to remove all the extensions. So let me do this. Let me go back into Python, and then let me initialize all my libraries. Then open the storage.h5 file for writing, for appending, right? Then I'm going to create the Tuscany group inside this file. So now inside this file, f1.root, I have the text file, right? Previously written with 4 lines, as well as the Tuscany group, which currently does not have anything inside of it, no objects, just the functions. And then I'm simply going to cycle through all 20 input files, and then going to copy each file into the similarly named node inside my HDF5 file, right? So done. I'm going to close my file, my HDF5 file, and then I'm going to remove all those small.png files from my file system, right? So now they're gone. And then I'm going to step inside. Actually, I'm going to do a pt-dump storage on H5, right? So actually see that those images now exist. They were written to the HDF5 file, and now they're actually in there, right? So those 20 images are inside the Tuscany folder or group inside my HDF5 file. So now if I go back into Python, I can now read them very easily, right? So I simply initialize all the libraries, and then I open the storage.h5 file for reading. And by the way, I should have displayed this file size. So just to show you that storage.h5 file, now it's 2.4 megabytes, because now it has those 20 images added to the Tuscany group. And now let's say I want to read image number 8. Well, I simply can use this notation as one of several possibilities, right? So image number 8, and then I'll simply say image show, and that will display the image. So here's image number 8. Let me read image, let's say number 15. You will see that it's a different image, right? So now it's image number 15, and so on. So you get the idea, right? So now we have all 20 images stored. I deleted them from the original file system, but now they're all stored inside the HDF5 file. And then again, there are many different ways you can dissect them. For example, you can cycle through them, this way, right? So I, cycle through all nodes, everything under Tuscany group, and then print some basic information about that node. So all these nodes were going to be images, and then I can, use this notation, I can use this notation, and so on. And then just a last example to show you that you can remove nodes and rename nodes as well. So currently, I think I have it in read mode. So let me reread the same data in append mode, so I can actually modify it. So here I'm reopening the same file in append mode, right? And then I'm going to remove one of the images. So I'm going to remove image number 19. So right now, if I do F1 root on Tuscany, Tuscany, and then display everything inside it, you see there are 20 images from 00 to 19, right? Okay, great. Now let me remove one of them, the last one. I'm just remove it like that. And then let me rename one of them. So small 18, I'm going to call last image, right? So I'm renaming the node. So now if I do F1 root on Tuscany, you'll see that now small 19 is missing because we removed it. And then small 18 was actually renamed to last image. All right. So this is everything I wanted to show. So current limitations of storing data inside, as file nodes inside an HDF file. There are some limitations. Of course, this is not a generic file system, not a file system like, normally you would be able to access in Linux. So this is a file system that's accessible only through Python commands that have, IO capabilities. So Python imaging library is one of them, but of course there are hundreds and hundreds of libraries that let you write data inside HDF5 file. So basically, whenever you use those, read-write routines from inside Python, instead of the file name, you will, or the file handle, you will pass the file node handle, right? Like F node in our examples and so on. And that will let you write and read data from, to and from the file nodes inside an HDF5 file. So naming restrictions, right? So only valid Python identifiers are valid. So, things like, dots, forward slashes, etc., are not allowed. So currently only binary IO is supported, but this is actually a good thing because the whole idea of HDF5 is very efficient storage. And this is done via NumPy, right? And NumPy stores data natively in binary format, and this binary format is then stored on disk with optional compression inside an HDF5 file. All right, so that's everything I wanted to show, and I guess now I will just open the floor to questions.